So my question is, how do we bring in more of the knowledge from physics into AI algorithms, right? That could be in the form of domain knowledge, like we know Newtonian laws of physics. How do we bring that into, say, an AI application about the world around us? Or it could be like algorithms and techniques that have been, I don't know why there is like a skip, right, with this mic. Is it better? No, now it's gone. Testing. Is it okay now? Yeah. Yeah. So as I said, it could be from simple laws of physics or equations that we know from studying extensively and doing experiments of the physical world around us. Or it could be like sophisticated algorithms that have been developed by physicists or in the area of physics, like tensor methods, for instance. How do we bring all that into machine learning algorithms and get better gains? Like better generalization is something that I will focus a lot on, because that's one of the mysteries of deep learning. And in practice, what we find is there's always kind of need for better generalization, right? So you will find that when you go to real applications, for instance, I'm now at Nvidia, and before that I was at Amazon Web Services. And so you will see models that will need to serve a range of applications. So there's one training data set and a range of other test sets that you want to serve the model on, and that's very different from classical analysis of machine learning, where training and test are the same IID distribution. So that's almost never true in practice. How do we build more knowledge from physics and other domains to better generalize when there is lack of enough training data to capture all the diversity of the problem? So that's something we can see. So I'll give you some use cases. Wow, so this one doesn't used to be working. I don't know what happened. So yeah, so I'll give you some examples. The first one is what I would say as neural programming, right? So this is a broad area where you want to ultimately have computers program themselves. I mean, that seems like science fiction, but you can ground the problem in terms of asking, suppose I give it a lot of input-output data, like, what you would like the program to output and what should the input to the program be, as well as some kind of rules or some kind of, very simple kind of specifications of the program. Can the rest of it be done by the computer itself, right? And if it sees enough examples of programs, can it then learn to write a new program? So that's a lofty goal, and we asked, how we can do this in a very simple context, which is the domain of mathematical functions. Suppose we give it, knowledge of how different mathematical functions are related to one another, as well as the input-output data, the numerical data of what these functions are within some range. Can it then learn what these functions are and generalize, right, across the domain of functions? So you also call this as meta-learning, a term that's especially popular these days, because you're not just learning one function, you're learning an entire domain of functions. So this, to me, is a very simple way to think of infusing physical knowledge or domain knowledge into a system, right? Because you're also specifying relationships between the functions that's known a priori. So it's not just a black box input and output that you want to learn, but you want to build more. And so this was our ICLR paper this year that said, how do you combine both knowledge from symbolic expressions or equations, as well as numerical data, which is the input-output data, together in a same framework to learn an entire domain of functions. And so, it's clear that knowledge of relationship between functions in a symbolic manner can really help you learn them better, right? Because if you just learn each function in isolation, so you just use a function fitting framework like a deep neural network to learn a function from input and output, you will miss more information about it. And particularly, you won't be able to extrapolate, right? So all these neural networks, what they're doing is just interpolation and not extrapolation. And so the only way to do that is if you can now learn relationships between all the functions in a domain, you can hope to generalize better and even extrapolate, right? And that's the goal of doing this by combining both symbolic rules as well as numerical data. And we'll see how you can express that through hierarchical structures or trees. Right, so you can think of many applications of this once you've learned such a domain of functions. You can complete equations, right? So you can now have a symbolic evaluation. And there are some that are already available, like SymPy, but they're all programmed. So the question is, can it learn in a flexible way from data itself? So verification, equation completion. You can also do more complex tasks like solve differential equations, solve integer programs. I mean, there's just such a broad array of applications once you're able to do this. So, so in this aspect of meta learning, you're not only learning different functions, but you also have different tasks, right? You're not aiming to just do one task, which is what typically a neural network is trained for. You just have one loss function that you want to optimize. But here, that's not the case. You have several different tasks you want to be simultaneously good at. And that's why it's important to learn them very well. So how do we use hierarchy or trees to represent this? So if you have like symbolic equations, so in our particular use case, we only looked at equations, but you can think of also expanding this to inequalities. So if it's an equation, you can think of having the left-hand side and the right-hand side, and I guess, let me see. Yeah, the left-hand side and, sorry about that. The left-hand side and the right-hand, it's a new pointer. The left-hand side and the right-hand side, and you want to have the equality, right? So the question is now if it's, you can compose different functions to form the left-hand side as well as the right-hand side. So it's like kind of, you're progressively composing simple functions to get each side of the equation, and you can represent it as a symbolic expression tree. So this is pretty clear, right? But then usually numbers, we don't think of using trees to represent them. But in this framework, we wanted to unify both numerical data as well as symbolic data. And we also want to be expanding to numbers that we've never seen before. Suppose the neural network is only trained on a limited domain and you want to expand the range on which you want to evaluate. You also want to understand what this new number means. And for that, we decided to express the numbers in the decimal system. You can use any base system, but here the idea is every time you think of expressing a number, you're using the decimal base to express exactly what that operation is, right? And so with this, now you can also think of evaluating functions using for any number, right? So the idea is ultimately with trees, you can represent both numbers as well as symbolic expressions. And so now you can jointly train both this information together. I mean, if you think about one of the challenges in machine learning is how to reconcile discrete data and continuous data. I mean, neural networks are primarily useful for continuous data, and it's tricky to think of discrete data, right? But now by using these kind of tree structures, we can make this modular and be able to overcome that. And this kind of modularity is also crucial because you see the same function, for instance, the addition or power, occurring in different contexts. So you understand what the relationships between different functions are, both on numerical data as well as symbolic data. And so the hope is with this, it can better learn what this function is really doing rather than just interpolating based on input and output. And and you can provide all kinds of rules, right? So you can say there is all the axioms of math, what is an equality or an inequality, what is transitivity, all these axioms you can use. You can also think of functions that involve one variable or two variables. So all these different rules and axioms you can build into your system. So you can start with a base set of axioms, and now you can artificially generate different expressions. So you can generate expressions of different depths and use that to train your machine learning model. And so the idea is ultimately you want to generalize to even higher depths, right? So you cannot keep training it on more complex equations because that's not computationally feasible. The hope is you can train up to some depth and then will it generalize beyond? And we have some beginning answers to that question. And so for now we use like trigonometric and basic algebra equations. So this is the most number of functions that were trained together or learned together in the neural programming domain. And there's always room to expand beyond this, but this was the start. And so for how do you now capture these hierarchies? I mean, since trees are the primary building block for this setting, we use tree LSTMs, right? So LSTM is the long short-term memory systems, and ultimately, like, our goal is to be able to learn the embedding or relationship of what each step in the tree is doing, right? So it could as well be some of the other memory networks, but LSTMs work fine in our case, and that's why we used it. And so the idea is if it's a verification one, like whether the equation is true or not in a symbolic case, we used like a 0-1 metric. But now if it is an evaluation, we use the square loss. And so depending on whether you're doing numerical data or symbolic data, you also use a different loss function to evaluate that. Which is natural, right? In one case, whether the equation is true or not. In the other case, you want to ask how close you are to the answer. And so you can use different loss functions while simultaneously training on both symbolic and numerical data. And so these are examples of what you can generate. You can, verify whether the identities are correct or incorrect once you've trained the system. And so what we found here was, there's a number of different, frameworks you can think of. There is the SymPy is like the baseline, right? At least one of the baselines. It's pre-programmed. You expect that this would do well, but it turns out that, especially as you are going to higher depth, it's not always very accurate. For instance, it's not able to say like a false equation whether it's really false. Like it doesn't, it's not able to always pick that out. And in a LSTM without a tree structure, you also expect it to do not very well. But the tree LSTM you see has pretty good accuracy. So here again, I want to differentiate just plain generalization from extrapolation, right? So when I say generalization, I mean the train and the test data sets have the same level of complexity. So in this case, it was verifying symbolic equations, so it's both of the same depth. Like you train up to equations of depth 3, you also test on equations only up to depth 3, right? Whereas extrapolation is now testing on, say, depth 4. And so there you see there is quite a big gap here with SymPy or LSTM, but the gap is quite low when it comes to tree LSTM. So the modularity is very crucial when you want to extrapolate and test on instances that are harder than what you trained on. And the other interesting thing is if you can do a tree LSTM just based on symbolic expressions, right? So you can, as I said, artificially generate a set of training examples based on symbolic equations, and you can train an LSTM, or you can combine it with numerical data. And you see that there is a jump between the two, right? So there is an improvement of when you use numerical data even for symbolic evaluation, which is interesting because you can think of numerical data as providing additional evidence of these symbolic relationships, right? So having diverse data of different kinds can actually help in training and generalizing better, which is what we see from this. So if you have like both numerical data and symbolic data in a domain, you want to combine the two. That's really the takeaway. And you can see that we can also complete different equations. And the top answers, there are actually multiple of them, right? They're all correct. So it's not just one correct answer, there are multiple ones because obviously, these are equations. And so you can also evaluate functions and get pretty good fit of the functions in addition to being able to verify and complete equations. So there's a whole range of different tasks you can accomplish with this. And so this was on the completion task. And so that's really the takeaway from this talk is, for this section, is to ask ourselves, how combining both symbolic and numerical data can help us learn an entire domain of function in a better way, as well as carry out multiple different tasks, whether it's the basic function fitting or symbolic evaluation such as equation verification and completion, how we can do better by using all the knowledge together. Right, and it turns out that tree LSTMs are a modular way to build that knowledge. And although I showed this for trigonometric functions, you can think of the same principle holding in any domain, right? You know, for instance, the laws of physics, and you have some numerical data. And if you also want to build in, say, you're not sure whether this model or the law is correct, you could also make it softer, like you don't have to hard code the rules. And that's what you will see here, right? We never hard-coded the rules that are present, and that makes it much more flexible to be able to learn and correct for discrepancies if there are in how you are assigning the rules to your system. And so we've now expanded to also solving differential equations because you can use the same principle also for differential equation solver, and we believe that this could also bring in knowledge of existing solvers as well as, in some cases it's closed form, in other cases it's not, right? There's only numerical data. So you can combine all that knowledge together, and so this is still a preliminary work, but at least for simple, I think this was a low depth, the ODE equations, we see a good promise of using tree LSTMs compared to SymPy and other baselines. So, yeah.
Mathematica does all these things. What's the learning element here?
So Mathematica is all pre-programmed, right? You've told like exactly these are the rules, whereas we've never.
So I guess I'm not getting a sense of what kind of rules you're trying to learn exactly.
I mean, all the set of relationships that's present in that domain.
So how big are the data sets?
So in this case, the tree's depth was about 3 or 4, and the test was like a slightly higher depth from that. So we have the details in the.
How many examples are you?
So about tens of thousands. Yeah. Yeah.
So also like going in a different. So for example, you give your system example data of derivatives of functions, and then you query like what's the derivative of a sine function, and then it guesses. I also find it difficult to
So let's do the simpler example, right, without the derivatives. So there it was just the equation. So you give equations like sine square plus cos square is 1. And so these are all up to some depth. You generate all, synthetically you generate these equations of different depth as well as negative examples, like of what are not equations. And you also have like, we evaluated the function at random points, and we also gave that information.
How do you verify, for example, like solving Navier-Stokes equations or something like that?
I mean, yeah, in that case we don't, right? So in these are known. So in this case, these were known examples. Yeah. So it'll be interesting for cases where you don't know the ground truth. Yeah. So as I said, the differential equations is still very preliminary. There's a lot of new challenges we'll have to uncover. For instance, one challenge is, if you have to construct a new function that's not just a simple function, right? It's a composition of various functions. You have to learn how to construct a tree at test time. And that's hard because trees are discrete, the search space is broad. So we haven't yet tackled those, but we have some ideas on how to do that. Yeah. So that was on the first part. So I want to now ask, what else can we learn from physics, right, in machine learning? And so as Lenka earlier said, tensors have been at the core of my research, and I'm very excited to see how there's so many connections to different areas of machine learning. And the latest one I've been thinking about is how to build that into our deep learning systems, right? Like what are opportunities to go beyond just linear algebra functions in our layers. I mean, when you say it's a TensorFlow or a tensor core, what it really means is the input and the output is a tensor, right? But there's no reason for the intermediate layers to be linear algebraic other than historic. I mean, we have very good linear algebraic libraries, so it makes sense that we build our first systems from there. But there are rich opportunities to go beyond and ask, with multilinear algebra and tensor algebra, what more can we do and what benefits does it give? And I'll give some examples of that. Right, so the idea of using tensors into our learning algorithms is very natural because data is multidimensional. If you think of images with RGB, that's like, there is the number of channels, width and height. If it's video, there's also the time element. If you have text and images, there's even more dimensions. So a lot of, like multidimensional data, it's natural to think of using tensors. Right? The other one is even if the data itself is not having too many dimensions, you can think of correlations in your data as also being multidimensional. So mostly we think of covariances or pairwise correlations, right? That's the first analysis you would do, like whether it's PCA or some similar component analysis. That's usually on pairwise information. But there's no reason to just limit to that. Especially when you have a lot more data, you can afford to think of using higher order correlations. And much of my earlier work was to ask how we can use tensor methods based on higher order correlations to learn about hidden variables. In a probabilistic modeling framework, how we can learn latent variable models. And so there is kind of the thinking of not just directly encoding the dimensions of data, but also the higher order correlations using tensors. So what are some simple examples of that? Right, so you can already see in a standard convolutional neural network, when it comes to fully connected layers, we are vectorizing the activations. So from convolution layers, you get three-dimensional activations. But then when it comes to fully connected layers, you flatten it into a vector and just do simple matrix multiplication. Right, so the very first thing you can think of is, why should we throw away this extra dimensionality information we have? Why not propagate it all the way to the end, and hopefully this will lead to a better network? And that's what we did. So the idea is, you maintain the three-dimensional structure even in the fully connected layers. So you contract the tensor on all three directions using learned weight matrices. So you learn the weights directly. And also, like in the last layer, the regression layer, we are doing a tensor regression where we maintain three-dimensional weights that are expressed in a Tucker low-rank form. That's a special kind of low-rank representation, and we are expressing with that. And so the idea is this way you can, come up with much less number of parameters in these layers compared to when it was flattened. And that's what we'll see, like there is a big range of rank where you can really save the number of parameters, right? So you can save as much as 65% of parameters in the fully connected layers and still not lose accuracy. So the idea is by maintaining simple multilinear operations in all the layers, in the fully connected layers, we can expect to have much more compact networks without losing accuracy. So this is one instance of using tensors. So in the second one, what we did was more to think about correlations in data, right? So the viewpoint is, one is to directly encode the dimensionality in our data into tensors. The other is to think of how to express higher order correlations. And in this case, it was for time series forecasting. So we have, the input, which are the examples of the time series, and the output is to predict the next few time steps. And in long-term forecasting, what you're doing is you also want to predict way into the future, and that's where it's challenging. I mean, the error can be building up very quickly when you're predicting way into the future. And so what we did was, in a standard LSTM or a RNN, which is a recurrent neural network, what you have are these hidden states that propagate forward. Right? But instead what we did was to take a window of hidden states and build a tensor train representation over their cross product. or the outer product. So the idea is now you're not just like kind of doing a simple linear transformation with the nonlinearity like ReLU, but you're taking really the higher order correlation of this. But if you directly looked at the higher order correlation, that's too high a dimension. Instead, you're doing the tensor train or the matrix product state, that's more in the physics parlays. That's low rank, and hence you can have a compact representation of higher order correlations. And we see that this gives you the benefit on two data sets we tried, was the traffic data set and the weather data set or the climate data set. And we see that especially this is the root mean square error. So when you go to a long-term prediction, you want to predict way into the future, you see that the tensor LSTM, the tensorized LSTM, has much more graceful degradation of error compared to the baseline LSTM. And so that's what we see in these two data sets. And the intuition is when you are keeping track of higher order correlations in your model, but in a low rank form, there is much more benefit that you can use, right? Because it's known that time series have long range correlations and high order correlations. So is there a better way to keep track of it? And that's what we find in this architecture using tensors. And so there is the Tensor Li Framework, which makes it easy to build and experiment with such networks. The idea is to really bring together more of the scientific community as well as the deep learning community, right? So have you can plug into different backends like NumPy or SciPy, but also PyTorch, TensorFlow, and MXNet. And with this, you can have like basic tensor operations as well as more sophisticated tensor algorithms, such as those for decomposition or regression. And we also have now added like for matrix product states. So there is, you can build this into different layers of your network and just train it end to end, right? So it makes it very convenient to experiment with new architectures. And there are lots of example notebooks, Jupyter notebooks that you can run with this. So, I encourage you to go check this out. So there's also like, as I said, the use of tensors in unsupervised learning of probabilistic latent variable models. And much of my earlier work was focusing on that. So I just want to give one example, which is the topic modeling. So in a topic modeling, what you want to do is automatically categorize documents into different topics, right? And in a document, there may not be just one topic, but multiple topics. So can you, without having any labeled examples, can you automatically learn this topics in documents? And what I had shown before was you can do this by looking at third order correlations. So if you look at co-occurrence statistics of how triplets of works occur across the document corpus and decompose those tensors, you can probably recover the underlying model, which is the latent Dirichlet allocation model. So, and you can also make this now scalable using a range of randomized linear algebra and multilinear algebra. And so what I built last year was a service in AWS, the Amazon Web Services, that makes use of this algorithm, and it's available on the cloud. So you can use this on SageMaker platform directly as the LDA algorithm, or use it in the Comprehend service, which is specifically built for text processing. So it has like kind of pre-processing layers that kind of directly take the text and output the topics, right? You can use it in both forms. And what we see is compared to open source baselines like Mallet, there is an improvement in terms of the training time it takes to learn these models at scale. So there is benefits we can use from our highly optimized linear algebra libraries, but also build new capabilities for expanding that to multilinear algebra and solve various machine learning problems in the process. So the third one, I think I'm mostly out of time, so I want to just quickly show you this example as how now we can use machine learning to tackle various physics problems, right? So in this example, we have a drone and we want to ask, can we teach it to land better. I mean, there are control algorithms that are designed for this, but can we improve upon that? And that's kind of the overarching goal of a new center we have at Caltech, which is the Center for Autonomous Systems and Technology, that aims to bring robotics and AI together and really, build better autonomous systems, right? As well as think of foundations for such a setting. And so you can think of various challenges for drones. If you are, there's fair bit of fluid dynamics we understand in ambient air, but anytime there is turbulence or ground effect, there's so much we don't, right? So for instance, when the drone is close to the ground, there is a complex interaction of the drone, its motors, along with the ground, right, or near a wall. And when there is a higher velocity, the drone is moving at a higher velocity, there's the air drag. And there could also be external wind conditions. So all these are now forces that are unknown. And so this is what we want to do at CAST and understand how to improve drone flights. For instance, I don't know why the video is distorted, but you can see like we have a unique drone testing facility where there are 1,300 programmable fans there. So you can generate different wind conditions and what you see is there and have precise measurements. We have an array of 40 cameras that can record this up to a few hundred microns. And so we can have very precise, reproducible experiments on the drones. And so now the question is how we can use this data for machine learning and how we can improve the drone flights. So, so far we only looked at the first problem, which is to ask what happens when the drone is close to the ground, right? We haven't got into external wind conditions, but that's the next step. And so here you can ask, okay, naturally I can use a neural network to learn the unknown ground effect, but there are still some challenges with that. So with the ground effect, the primary unknown is the external aerodynamic force, like this force that's created because the drone is interacting with the ground. Usually there's also the unknown moments that are, that need to be learned, but in the case of ground effect, that's not a prominent one, so we didn't learn that one. And so if you just use a neural network as it is, it's not going to work. In fact, we had examples of the drone crashing if you just trained it on a plain neural network, right? So, and the reason for this is because, first of all, like neural networks by themselves could be unstable. We don't know what it has learned, how it can generalize to new conditions. And so how, putting that in the loop of a control algorithm without any checks and balances is really a recipe for disaster, as we actually found when we tried to fly the drone, right? So instead we came up with a simple spectral normalization technique where we normalize the spectrum of every layer of the neural network, which limits the Lipschitz constant. So with this you can bound the Lipschitz constant, and that way you can actually now guarantee stability, right? So in the sense of Lyapunov analysis, we can guarantee stability. And this is actually what worked in practice. So the theory and practice actually aligned well together in this example. So I just want to show quick demos. And so on the left, you will see just the PD baseline controller without learning. On the right, you will see the neural lander. So if you see like both took off, this is just one dimension, just go up and come down. And so now if you see here, it's still hovering, it's already landed, right? So that was kind of the, how you can see the same with 3D here. On the left is the PD and the right is the neural. So with the 3D, we are kind of going it at an angle and coming back. So you will see again. So there you see it's going up at an angle, and now watch as it tries to land. Right, so that already landed, it's still hovering. And so that's the idea that with, like now simple learning algorithms, you can improve this, yeah. So it's learning, it's only correcting for the unknown force, the aerodynamic force. So the rest of the physics model is as it is, right? It's only adding that residual and then building that into the controller. So, and that's kind of the idea, not to black box learn everything, use our domain knowledge and only correct for the unknown residuals. And so that was important. So I also want to point out now at Nvidia, there's lots of opportunities for intersection of physics and machine learning. For instance, you may have heard of like the exascale effort to really do large-scale physics simulations as well as machine learning. And this was at the Oak Ridge Laboratory. The Summit supercomputer was able to beat the XOPS, in terms of the number of operations. And GPUs are really at the middle of all this, right? So there's lots of exciting opportunities, as well as a very rich research environment at Nvidia, interdisciplinary in a number of ways. So I've just joined, so I'm very excited to build new open publishable efforts there in core machine learning, but also how it connects to different areas. So if you have students both for full-time as well as internships, we also have postdoctoral opportunities as well as a new AI residency program we're going to launch. So there's a whole range of efforts as well as collaborative efforts with faculty and faculty visits. So we have, I'm really looking forward to growing this more at Nvidia. And so I know I'm out of time. The idea is really how we can bring physics and machine learning together, and there are lots of rich opportunities there. Thank you so much.